What if everything we know about crossing the vast emptiness of space is about to change? Picture this. You take a single step through an invisible gateway and find yourself standing beneath an alien sky, light years from home, in less time than it takes to blink. This isn't just science fiction. Wormholes, those mysterious tunnels through spacetime, might hold the key to unlocking instantaneous travel across the universe. And the most thrilling part, the science behind them is stranger and more awe-inspiring than anything Hollywood could dream up. From the equations scribbled by Einstein over a century ago to the mind-bending frontiers of quantum physics today, the possibility of cosmic shortcuts isn't just a fantasy. It's a puzzle that the greatest minds on Earth are racing to solve. Think about the sheer scale of our universe for a moment. Even with our fastest rockets, reaching the nearest star would take tens of thousands of years. But what if we could fold space itself, creating a bridge between two distant points? That's the promise of wormholes, a concept so revolutionary it could rewrite the rules of exploration. Imagine civilizations spanning galaxies, not confined by the slow crawl of light speed. Picture a future where humanity isn't bound to a single corner of the cosmos, but free to wander the stars as easily as we cross continents today. It sounds impossible, yet the math suggests it might not be, and that's where things get truly fascinating. In this journey, we're diving deep into 30 of the most groundbreaking theories about wormholes and instantaneous travel. We'll explore how black holes might hold the secret to stabilizing these cosmic passageways, why exotic matter could be the glue that holds them open, and how quantum entanglement might blur the line between science and magic. Along the way, you'll discover why some physicists believe wormholes could already exist hidden in plain sight, and how we might one day harness them to leap across the universe. So if you've ever stared up at the night sky and wondered what's really out there, get ready. The answers are closer and more extraordinary than you ever imagined. To understand why wormholes captivate scientists and dreamers alike, we need to start with the fabric of reality itself. Space isn't just an empty stage where planets and stars move. It's a dynamic, stretchable material, warped by gravity like a trampoline bent under the weight of a bowling ball. Now imagine pinching two distant points of that trampoline together until they nearly touch. That's the essence of a wormhole, a shortcut where the immense distances we see in space collapse into a tunnel you could theoretically traverse in moments. The idea isn't just speculative fantasy. Back in 1935, Albert Einstein and physicist Nathan Rosen used the equations of general relativity to show how these bridges might form. Their work revealed something astonishing. Black holes, those cosmic vacuum cleaners, could theoretically pair with their mirror opposites, white holes, creating a tunnel between them. But here's the catch. Without some cosmic glue to hold it open, this tunnel would snap shut faster than you could say, interstellar road trip. The gravitational forces at play would crush anything trying to pass through, turning your quick hop across the galaxy into a one-way trip to oblivion. This is where exotic matter comes into play, a hypothetical substance with negative energy that could prop the wormhole open like scaffolding in a mine shaft. Unlike normal matter, which attracts via gravity, exotic matter would repel, counteracting the tunnel's natural tendency to collapse. It sounds like something straight out of a physicist's wish list, but quantum mechanics hints that such weird energy might not be impossible. Tiny amounts of negative energy already show up in lab experiments, like the Casimir effect, where two metal plates in a vacuum somehow pull toward each other due to quantum fluctuations. Scaling that up to stabilize a wormhole, that's the trillion-dollar question. And then there's the elephant in the room. Even if we found or built a stable wormhole, where would it lead? The math allows for connections not just across space but across time, raising wild possibilities. Step through one end, and you might emerge centuries in the past or future. It's a concept that blurs the line between astrophysics and time travel paradoxes, making wormholes as much a philosophical puzzle as a scientific one. Yet for all their potential, wormholes remain ghosts in the equation's elusive, unproven, and shrouded in what-ifs. No telescope has ever spotted one, and creating one would require energies and technologies far beyond our grasp. But that's the beauty of theoretical physics. It gives us a playground to explore the universe's deepest mysteries, even if the answers lie just beyond our reach for now. And as we'll see in the theories ahead, that playground is far stranger than we ever imagined. Albert Einstein's name is synonymous with reshaping our understanding of the cosmos, but few realize just how deep his fingerprints are on the wild idea of wormholes. In 1935, while most of the world was fixated on earthly concerns, Einstein and his colleague Nathan Rosen published a paper that would quietly revolutionize theoretical physics. They weren't setting out to invent cosmic shortcuts, they were simply wrestling with the equations of general relativity, trying to make sense of black holes. What they stumbled upon was far stranger, a hidden doorway in the math suggesting that spacetime could curve so drastically it might stitch together distant regions like a thread pulled taut through fabric. At its heart, their discovery was about gravity's grip on reality. Einstein had already shown that massive objects like stars warp spacetime, creating the curves we perceive as gravity. But the Einstein-Rosen bridge, later nicknamed the wormhole, revealed something even more radical. If space could bend, why couldn't it fold? Picture a sheet of paper representing the universe. Draw two dots far apart, that's the exhausting journey light would take across flat space. Now fold the paper until the dots touch. Suddenly, the distance collapses. That's the elegance of their insight. The universe might have built in loopholes where physics cheats distance itself. Yet there's a reason we're not booking wormhole vacations yet. Einstein and Rosen's original concept had a fatal flaw. Their theoretical tunnel was catastrophically unstable, snapping shut instantly under its own gravitational weight. Imagine stepping onto a bridge that crumbles beneath you the moment you take your first step. That's what would happen to any traveler daring enough to enter one of these raw, unrefined wormholes. But here's where modern physics picks up the thread. Today's researchers see Einstein's work not as a dead end, but as a starting point, a clue that nature might allow these shortcuts if we can just find the right tools to stabilize them. The legacy of that 1935 paper echoes through labs and lecture halls even now. When scientists talk about traversable wormholes, they're standing on the shoulders of Einstein's math, asking questions he might never have dreamed of. Could exotic matter, with its repulsive gravity, act as cosmic duct tape to hold these tunnels open? Might quantum effects, flickering at the smallest scales, provide the scaffolding needed to make them safe for passage? These aren't just thought experiments. Cutting-edge projects like quantum gravity research and high-energy particle experiments are, in essence, testing the boundaries of Einstein's intuition nearly a century later. What's often overlooked is how prescient Einstein was about the rules of the game. He famously dismissed the idea of spooky action at a distance in quantum mechanics, yet his own equations hinted at phenomena just as bizarre. Wormholes, if they exist, would challenge our notions of cause and effect, distance, and even time. They're a reminder that the universe's rulebook is far stranger than our everyday experience suggests. And that's why Einstein's work remains indispensable, not because he had all the answers, but because he taught us how to ask better questions. The next breakthrough in interstellar travel might not come from discarding his theories, but from peeling back another layer of their hidden possibilities. One of the most tantalizing ideas in modern physics is the concept of traversable wormholes, cosmic tunnels you could actually travel through without being crushed into oblivion. But here's the catch: nature seems dead set against making it easy. Left to their own devices, wormholes predicted by general relativity snap shut faster than a mousetrap, collapsing under their own gravitational forces before anything could pass through. That's where exotic matter comes in, a theoretical substance so bizarre it flips the laws of physics on their head. Unlike ordinary matter, which responds to gravity by pulling objects together, exotic matter would push back with negative energy, acting like anti-gravity scaffolding to prop a wormhole open. Imagine trying to hold open a doorway made of quicksand. Every time you push against one side, the other collapses unless you have some kind of repulsive force counteracting it. That's essentially the role exotic matter would play. The catch: we've never actually observed this stuff in nature. It exists in equations as a mathematical possibility, a loophole in quantum field theory that allows for regions of negative energy. But here's where things get weirdly promising. Tiny glimpses of this phenomenon might already exist in the quantum realm. Take the Casimir effect, where two uncharged metal plates placed incredibly close together in a vacuum experience an invisible force pulling them together. It happens because the space between them suppresses certain quantum fluctuations, creating a subtle imbalance, a whisper of negative energy. The problem: scaling that up to the cosmic level would require unimaginable amounts of this exotic material. Some calculations suggest you'd need the negative energy equivalent of an entire star's mass just to stabilize a wormhole mouth wide enough for a single atom to pass through. And that's before tackling the engineering nightmare of shaping and controlling it. Yet physicists aren't ready to dismiss the idea entirely. A handful of bold theories suggest workarounds, like lining the wormhole's throat with ultra-thin layers of exotic matter, or harnessing quantum effects we don't yet fully understand. The deeper you dig, the more exotic matter feels like a cosmic placeholder, a label for whatever weird physics we're missing. Some models even speculate that dark energy, the mysterious force accelerating the universe's expansion, might share properties with this hypothetical material. Could the same repulsive effect driving galaxies apart also hold the key to interstellar shortcuts? It's a long shot, but that's the thrill of frontier science. Every unanswered question is an invitation to rethink the impossible. For now, exotic matter remains a dazzling what-if at the edge of known physics, one that keeps the dream of wormhole travel alive, even if it's still light years beyond our grasp. What if the spooky, invisible threads linking entangled particles were actually tiny wormholes hiding in plain sight? This is the radical idea behind one of the most exciting theories in modern physics: ER equals EPR. At first glance, it sounds like alphabet soup, but this equation represents a potential bridge between two pillars of science that have stubbornly refused to connect: Einstein's general relativity and the bizarre rules of quantum mechanics. The story starts with two of Einstein's own discoveries, oddly at odds with each other. In 1935, he and Rosen proposed those theoretical wormholes we call Einstein-Rosen bridges. That same year, with colleagues Podolsky and Rosen, he famously critiqued quantum entanglement, the phenomenon where two particles become mysteriously linked, instantly mirroring each other's states no matter how far apart they are. Einstein called it spooky action at a distance, convinced it revealed a flaw in quantum theory. Fast forward nearly a century, and physicists like Juan Maldaisner and Leonard Susskind have flipped the script. What if entanglement and wormholes aren't separate puzzles, but two sides of the same cosmic coin? Here's where it gets wild. The ER equals EPR conjecture suggests that every pair of entangled particles might be joined by a microscopic wormhole, a Planck-scale tunnel threading through the fabric of spacetime. Think of it like this: when particles become entangled, it's not some ghostly signal traveling between them. Instead, space itself could be subtly warped, creating an invisible shortcut that binds them together. It's as if the universe cheats distance by folding the rules at the tiniest scales. Now, before you picture hopping into a wormhole the size of an atom, there's a crucial catch. These hypothetical tunnels would be unimaginably small, trillions of times tinier than an atomic nucleus. Scaling them up for human travel would require energies and technologies we can barely fathom. But the implications are staggering. If spacetime and quantum entanglement are truly intertwined this way, it could rewrite our understanding of reality's deepest layers. The theory also hints at something even more profound. Wormholes might not just be cosmic shortcuts. They could be the universe's way of enforcing quantum connections. In this view, entanglement isn't spooky at all. It's spacetime's architecture working exactly as designed, with hidden threads stitching together what appears separate. That's the kind of elegance physicists dream about, a single framework explaining both the vast curvature of galaxies and the flickering oddness of quantum particles. Of course, this remains speculative. No one's observed a wormhole, let alone confirmed its link to entanglement. But experiments are inching closer. Quantum computers manipulating entangled qubits might inadvertently reveal clues about spacetime's structure. Gravitational wave detectors could uncover anomalies hinting at hidden tunnels. Every new discovery in quantum gravity brings us closer to testing whether ER truly equals EPR, and whether the universe's most mysterious phenomena are secretly connected. What makes this theory so compelling isn't just the sci-fi allure of wormholes. It's the possibility that two seemingly unrelated corners of physics might finally shake hands. If entanglement really is spacetime's way of whispering across distances, then the universe is far more clever and far more interconnected than we ever imagined. And that's a revelation worth chasing, no matter how small the wormhole. Black holes have long been painted as the universe's ultimate dead-ends, cosmic traps where matter and light vanish forever, crushed into oblivion by unimaginable gravity. But what if we've been wrong about them all along? A daring faction of physicists is challenging this grim narrative, proposing something far more thrilling. Black holes might not be endings at all, but gateways. Not pits, but portals. The idea hinges on a radical reinterpretation of Einstein's equations, suggesting that the terrifying singularity at a black hole's heart could actually be the mouth of a wormhole, threading through spacetime to another place, or even another time. Think of it like a cosmic Möbius strip. From the outside, a black hole appears as a one-way street into darkness, but twist the math just right, and that same object could become a tunnel. Its crushing gravity not a barrier but the very force holding the passage open. The key lies in what happens beyond the event horizon, the point of no return. Classical physics says everything inside gets shredded into infinity, but some quantum gravity models hint at alternatives. Imagine the singularity isn't a destructive endpoint but a bridge, warping spacetime so severely that it pinches together distant regions like a folded sheet of paper. This isn't just speculative daydreaming. Certain solutions to Einstein's equations, like the Kerr metric describing rotating black holes, suggest their interiors might avoid true singularities altogether. Instead, they could harbor inner horizons where space flips inside out, potentially leading to other universes or distant corners of our own. It's as if nature built emergency exits into these cosmic monsters, hidden behind layers of extreme physics. Even Hawking radiation, the faint glow black holes emit, hints at quantum weirdness that might preserve information rather than obliterate it, leaving room for tunnels instead of tombs. But before you pack your bags for a black hole vacation, there's a glaring problem: traversal. The gravitational tides near a black hole's entrance would stretch you into a spaghetti strand long before you reached any hypothetical wormhole throat. And if you somehow survived, there's no guarantee the tunnel would be stable or lead anywhere hospitable. Some models suggest these passages are riddled with chaotic turbulence or quantum firewalls, deadly obstacles that make the journey more theoretical than practical. Yet the possibility refuses to die. Advanced civilizations, some theorists argue, might harness black holes as natural wormholes by manipulating their spin or charge, effectively steering the tunnel's exit. Others propose that primordial black holes, tiny leftovers from the Big Bang, could house traversable wormholes too small for stars but just right for quantum information, acting as nature's own entanglement highways. What makes this theory so electrifying isn't just the sci-fi imagery. It's the way it forces us to rethink fundamental assumptions. If black holes and wormholes are two faces of the same phenomenon, then the universe's most destructive forces might also be its greatest connectors. The same gravity that tears stars apart could be weaving hidden threads through the cosmos, stitching together realities we've yet to imagine. And that's a twist even Einstein might not have seen coming. If black holes are the universe's relentless vacuum cleaners, then white holes are their rebellious twins, cosmic fire hydrants blasting matter and energy outward with unstoppable force. These hypothetical objects flip the script on everything we know about gravity, acting as one-way exits where nothing can enter, only explode forth. The math behind them is just as elegant as it is bizarre. While black holes trap even light behind an event horizon, white holes have an event horizon that works in reverse, ejecting everything inside while barring entry. It's like a door that only swings outward, hurling whatever's behind it into the cosmos. White holes emerge naturally from the same equations that describe black holes. Einstein's general relativity doesn't care which direction time flows, so the math allows for both possibilities. Some physicists speculate they could be the other end of a wormhole, the cosmic out door to a black hole's in. Picture a tunnel where one side greedily devours stars while the other spews them out, perhaps in a distant galaxy or even an entirely different universe. The idea isn't just poetic symmetry, it's a potential solution to one of the biggest mysteries about black holes. Where does everything they swallow actually go? Yet for all their theoretical allure, white holes face a glaring problem. We've never definitively observed one. If they exist, why are they so elusive? One explanation is that they're incredibly short-lived. Unlike black holes, which can feast for eons, white holes might self-destruct the moment they form, erupting in a catastrophic burst of energy before collapsing under their own instability. Another possibility is that they're hiding in plain sight. Some researchers suggest that gamma-ray bursts, the most violent explosions in the universe, could be the death throes of white holes, their final screams as they expel their contents in a blinding flash. Then there's the wilder notion that white holes aren't just rare, they're time-reversed black holes. In this view, a white hole is what a black hole becomes if you run the cosmic clock backward, like rewinding a video of a collapsing star until it explodes instead. This idea blurs the line between past and future, suggesting that the universe's most destructive objects might have a second act we've never witnessed. Whether they're wormhole exits, time-flipped black holes, or something even stranger, white holes force us to confront the limits of our physics. they're a reminder that the universe might not play by the rules we're used to, and that the most outlandish ideas could still be waiting in the equations, daring us to look closer. We've been thinking about wormholes all wrong, not as tunnels in our familiar 4 dimensions, but as structures woven through the hidden folds of reality itself. String theory, the ambitious framework attempting to unify all fundamental forces, suggests our universe might have up to 10 or 11 dimensions, with the extra ones curled up so tightly we'd never notice them. It's like ants crawling across a telephone wire. From their perspective, they're moving along a one-dimensional line, oblivious to the vast 3-dimensional space around them. Now imagine if wormholes weren't just shortcuts through space and time as we know them, but bridges through these higher dimensions, completely invisible to our limited perception. This isn't just a wild speculation, it's a mathematical possibility that redefines what interstellar travel could look like. In higher dimensional space, the rules of geometry change. Distances that seem insurmountable in our 4-dimensional spacetime might be mere steps away when viewed through the lens of extra dimensions. Picture a maze drawn on flat paper. From within the maze, the path seems long and winding, but from a 3-dimensional perspective, you could reach the exit by simply folding the paper. Higher dimensional wormholes could work the same way, allowing civilizations to bypass the constraints of our universe's apparent vastness. The implications are staggering. If such pathways exist, they might explain why we've never detected wormholes in our own dimensional slice. They're tucked away in directions we can't access or measure. Advanced civilizations, if they've mastered the physics of higher dimensions, could be using these hidden tunnels as a cosmic subway system, traveling undetected right under our noses. Some theorists even suggest that dark matter, the invisible stuff shaping galaxies, might interact with these extra dimensions, leaving faint fingerprints of their existence in gravitational anomalies we've yet to fully decipher. But here's the catch. Proving any of this would require technology far beyond our current grasp. We'd need instruments sensitive enough to detect distortions in spacetime at scales smaller than an atom, or experiments powerful enough to momentarily unravel hidden dimensions. Particle colliders like the Large Hadron Collider have searched for evidence of extra dimensions by hunting for missing energy particles that might briefly vanish into higher dimensional space, but so far, the results are inconclusive. Yet the idea refuses to fade. If higher dimensional wormholes are real, they'd rewrite not just our understanding of travel, but of reality itself. The universe might be far more interconnected than we ever imagined, with layers of existence just beyond our reach. And that raises a tantalizing question. Are we alone, or is the cosmos buzzing with activity we simply can't see? The answer might be hiding in dimensions we've yet to explore. The idea of stepping through a wormhole and emerging in another era isn't just the stuff of blockbuster movies, it's a genuine possibility lurking in the equations of general relativity. Wormholes don't just bend space, they twist time itself, offering a potential shortcut not just across the cosmos, but across centuries. Imagine a tunnel where one end sits near Earth today, while the other drifts near a black hole where time crawls to a snail's pace. Step through, and you might find yourself decades or even millennia in the future, all because gravity's grip on time is stronger near the black hole. This isn't fantasy, it's physics rooted in Einstein's revelation that time isn't absolute. It's elastic, stretching and compressing under the weight of massive objects. But here's where things get messy. If wormholes can connect different times, they open the door to paradoxes that could unravel causality itself. The classic grandfather paradox looms large. What if you traveled back and accidentally prevented your own birth? Some physicists argue the universe might enforce consistency. rerouting events to prevent contradictions like cosmic traffic control. Others propose that branching timelines could sprout with every jump, creating alternate realities where every possible outcome plays out. It's a dizzying thought. Wormholes might not just be time machines, but reality splitters, fracturing history into infinite parallel threads. Yet the biggest hurdle isn't just paradoxes, it's stability. Time-traveling wormholes would require conditions even more extreme than their spatial counterparts. Exotic matter would need to prop them open while resisting the chaotic feedback loops of time dilation. Even a slight imbalance could snap the tunnel shut or hurl travelers into random eras with no way home. And then there's the eerie possibility of closed time-like curves, paths through spacetime that loop back on themselves, trapping you in an infinite repeat of the same moments like a cosmic record stuck on replay. Despite the challenges, the implications are irresistible. Wormholes could explain mysteries like the Fermi Paradox, why we haven't met time-traveling tourists from the future. Perhaps they're forbidden by some undiscovered law of physics, or maybe they're hiding in plain sight, their effects too subtle for us to detect. Either way, the mere possibility reshapes how we think about time, turning it from an unyielding arrow into a labyrinth of potential shortcuts and detours. And that's the real magic of these theoretical tunnels, not just where they might take us, but how they force us to rethink the very fabric of reality. The idea of building a wormhole from scratch sounds like something straight out of a supercharged sci-fi novel, but what if it's not as far-fetched as we think? Forget stumbling upon a cosmic shortcut. Imagine engineering one, bending spacetime to our will with technology so advanced it borders on magic. This is the tantalizing promise of artificial wormholes, a concept that pushes the limits of theoretical physics and human ingenuity. The math doesn't forbid it. In fact, the equations suggest that with enough energy and the right materials, we might one day stitch together the fabric of the universe like master tailors, sewing tunnels between distant stars. But let's be clear, enough energy here isn't just flipping a switch. We're talking about harnessing forces rivaling those of collapsing stars or tapping into exotic matter we've yet to discover or synthesize. Picture a civilization capable of manipulating gravitational fields like clay or bending quantum fields to their will. Some models estimate that stabilizing a wormhole wide enough for a spacecraft would require negative energy densities equivalent to converting Jupiter entirely into pure energy, and that's just the power bill. The engineering challenges are even more daunting. You'd need to prevent the wormhole from collapsing the moment it forms, shield travelers from lethal tidal forces, and ensure the exit doesn't dump you into a star or the vacuum of deep space. Yet history's full of technologies that seemed impossible until they weren't. Take nuclear fusion. A century ago, smashing atoms together to release energy was a pipe dream. Today, labs like ITER are inches away from achieving sustained fusion reactions. Or consider quantum computing, once a fringe idea, now a reality with machines solving problems classical computers can't touch. The lesson: today's physics-defying megaprojects could be tomorrow's mundane tools. The real wild card is exotic matter. If it exists, or if we can engineer it, this strange substance with negative energy could be the linchpin holding artificial wormholes open. Think of it as cosmic duct tape counteracting gravity's crushing grip. Labs have already glimpsed whispers of negative energy in quantum experiments, like the Casimir effect. Scaling that up to interstellar proportions is a leap, but not an unthinkable one. And then there's the ultimate question. If building wormholes is possible, why haven't we met any aliens who have done it? Maybe the energy costs are too steep even for advanced civilizations. Or perhaps stable wormholes require conditions so precise they're practically impossible to achieve. Then again, maybe we're just not looking in the right places. Wormholes could be hidden in plain sight, disguised as black holes or lurking in higher dimensions beyond our perception. What makes this theory so electrifying isn't just the engineering challenge, it's the audacity of the premise. Artificial wormholes force us to confront the boundaries of possibility, asking not just, can the universe do this? But can we? They blur the line between nature and invention, suggesting that the greatest cosmic shortcuts might not be found but forged, and that's a vision of the future worth reaching for. Dark energy is the universe's greatest unsolved mystery, an invisible force stretching space-time apart faster and faster, as if the cosmos itself is in a hurry to disappear. Yet what if this enigmatic energy isn't just pushing galaxies away but also hiding a secret connection to wormholes? The math reveals something startling. The same repulsive force driving the universe's expansion might hold the key to propping open cosmic shortcuts. Think of it like this: dark energy behaves like anti-gravity on a colossal scale, counteracting the pull of matter. If we could harness even a fraction of that outward pressure, it might provide the perfect counterbalance to a wormhole's natural tendency to collapse under its own gravity. But there's a catch. While dark energy's repulsive nature seems tailor-made for stabilizing wormholes, its sheer uniformity makes it a double-edged sword. Unlike exotic matter, which could theoretically be concentrated around a wormhole's throat, dark energy is spread thinly across the entire universe. It's like trying to inflate a specific balloon in a room where the air is evenly dispersed. You'd need a way to gather and focus it. Some models suggest that regions of intensified dark energy, like those near cosmic voids or ancient quasars, might naturally warp spacetime in ways that favor wormhole formation. Others propose that advanced civilizations could manipulate dark energy fields, creating localized surges strong enough to forge traversable tunnels. The plot thickens when we consider dark energy's wildcard. Its density. Unlike matter, which dilutes as the universe expands, dark energy appears to maintain a constant density over time. This strange property means its influence grows as space itself stretches, a feature that could either stabilize wormholes for eons or unpredictably destabilize them. Imagine a bridge that gets stronger the longer it stands, but also more prone to sudden, catastrophic snaps as the fabric of reality stretches thin around it. Yet the most tantalizing idea is that dark energy and wormholes might be two sides of the same cosmic coin. Some unified field theories speculate that both phenomena stem from fluctuations in the quantum vacuum, the seething energy of empty space itself. If true, then wormholes aren't just holes punched through spacetime. They're dynamic structures woven into the universe's accelerating expansion, like ripples in an inflating balloon. That would mean the very force tearing the cosmos apart could also be stitching it together in hidden ways. Of course, this remains speculative. No one's detected a wormhole, let alone proven its link to dark energy. But upcoming telescopes like the Vera Rubin Observatory and experiments probing the nature of dark energy could uncover anomalies, subtle gravitational lensing or unexpected voids that hint at these invisible tunnels. Until then, the connection lingers as one of physics' most provocative what-ifs, that the universe's greatest destructive force might also be its ultimate architect of shortcuts. And if that's true, then the key to interstellar travel has been hiding in plain sight all along, woven into the very fabric of the expanding darkness around us. Cosmic strings are like the universe's forgotten threads, ghostly remnants of the Big Bang, thinner than an atom yet denser than a neutron star, stretching across billions of light years with gravity so intense they could warp spacetime itself. These bizarre relics are more than just theoretical curiosities. They might be nature's own blueprint for wormholes, weaving hidden tunnels through the cosmos without any need for exotic matter or black holes. Picture a spider's silk under tension so taut that it distorts the surface it rests on. Now imagine that silk is a filament of pure energy left over from the universe's first moments, pinching space-time around it until two distant points touch. That's the breathtaking possibility cosmic strings bring to the table. The math behind this idea is just as elegant as it is mind-bending. When two cosmic strings move past each other at near light speeds, their immense gravitational fields could twist space-time into a closed loop, a temporary wormhole. It's like dragging two fingers through the surface of a pond until the water folds over, creating a momentary bridge between separated points. Unlike black hole-based wormholes, these wouldn't require navigating lethal singularities or event horizons. Instead, they'd be cleaner, more geometric shortcuts, their stability borrowed from the string's own unimaginable density. But there's a catch. Cosmic strings, if they exist at all, are nearly impossible to detect. They'd leave faint fingerprints in the cosmic microwave background, the afterglow of the Big Bang, or cause double images of distant galaxies through gravitational lensing. Some astronomers have scoured the skies for these anomalies, hoping to spot the subtle warping that would betray a string's presence. So far, no smoking gun. Yet the hunt continues, because finding even one cosmic string could revolutionize our understanding of spacetime's architecture. What makes this theory so compelling isn't just the potential for wormholes, it's the sheer longevity of these cosmic threads. A single string could outlast stars and galaxies, surviving virtually unchanged from the universe's infancy to its distant heat death. If advanced civilizations exist, they might seek out these ancient filaments as ready-made transportation networks, tapping into spacetime's primordial wrinkles to hop between galaxies. It's a humbling thought. The same structures that emerged in the first fractions of a second after the Big Bang could still be threading the universe together today, hidden highways waiting to be mapped. Of course, the practical challenges are staggering. Harnessing a cosmic string would require technology capable of moving these ultra-dense objects, or waiting millennia for them to align just right. And even then, the wormholes they form might be fleeting, snapping shut faster than a spacecraft could traverse them. But in a cosmos where the improbable often becomes inevitable, cosmic strings remind us that the universe might have already built the shortcuts we're dreaming of. We just have to learn how to read the stitches. What if the entire universe is just an illusion, a cosmic mirage projected from the edges of reality itself? This is the mind-bending premise of the holographic principle, a theory suggesting that everything we perceive, the stars, galaxies, even the space between them, might be nothing more than a three-dimensional movie playing on a two-dimensional surface at the edge of the cosmos. And if that's true, then wormholes could be something even stranger. Glitches in the code, shortcuts stitched into the fabric of the projection. Think of it like a video game. The world you explore on screen feels vast and immersive, but under the hood, it's all rendered from lines of code on a flat, two-dimensional chip. Now imagine scaling that up to the universe. The holographic principle proposes that all the information about our three-dimensional reality, every particle, every force, is somehow encoded on a distant, two-dimensional boundary, like a cosmic DVD. Wormholes, in this view, wouldn't be tunnels through space but errors or backdoors in the projection, places where the simulation skips a step. It's as if the universe buffered for a moment, leaving a gap you could slip through. This idea isn't just philosophical musing. It emerges from black hole physics, specifically the work of Jacob Bekenstein and Stephen Hawking, who discovered that the information swallowed by a black hole is proportional to its surface area, not its volume. That odd detail hinted that reality might store its data on surfaces, not in volumes like a hologram where a flat image creates the illusion of depth. If the universe follows similar rules, then wormholes could be nature's way of compressing that data, linking distant points in the projection without traversing the space between them. The implications are staggering. A holographic wormhole wouldn't just bend space, it would rewrite the rules of existence. Traveling through one might feel less like moving and more like teleporting, as if the universe recalculated your position in the cosmic code. Some models even suggest these shortcuts could explain quantum entanglement, where particles instantly influence each other across vast distances. In a holographic universe, that spooky connection might just be 2 points sharing the same line of code. But here's the twist: proving any of this would require detecting the universe's pixel size, the smallest possible unit of spacetime. Experiments like the holometer at Fermilab have searched for faint jitters in reality that might betray its digital nature, so far without success. And even if the holographic principle is true, harnessing its shortcuts would mean understanding reality at a level we can barely fathom, like a character in a game trying to hack the console running it. Yet the theory refuses to fade because it solves some of physics' biggest headaches. It bridges the gap between quantum mechanics and gravity, suggests a way to unify all forces, and most tantalizingly hints that the universe's greatest mysteries might not be out in the stars, but in the very nature of reality itself. Wormholes, if they exist, could be more than cosmic shortcuts. They might be proof that we're living in a projection, and that somewhere, just beyond the edges of perception, the real code awaits. Neutron stars are nature's most extreme pressure cookers, stellar corpses so dense that a single teaspoon of their material would weigh 1 billion tons on Earth. But hidden within that unimaginable crush of matter, something even stranger might lurk: microscopic wormholes twisted into existence by the sheer force of gravity. Picture the core of a neutron star, where atoms are squeezed so tightly that electrons and protons merge into a sea of neutrons, all pressing inward with unfathomable pressure. Under these conditions, spacetime itself might warp in ways we're only beginning to understand, creating fleeting tunnels so small they'd make a grain of sand look like a planet. The math behind this idea is as elegant as it is speculative. General relativity tells us that extreme curvature of spacetime can, in theory, pinch together distant regions like folding a piece of paper. In the chaotic aftermath of a supernova, the explosion that births a neutron star, quantum fluctuations and gravitational shockwaves might briefly stitch together microscopic wormholes, connecting the star's core to other points in spacetime. These wouldn't be the grand, traversable tunnels of sci-fi. They'd be more like quantum-scale cracks in reality, flickering in and out of existence too quickly for anything larger than a subatomic particle to slip through. Yet even these tiny portals could have colossal implications. If they exist, they might offer a solution to one of neutron stars' biggest mysteries: what happens at their cores. Some models suggest the pressure inside a neutron star could be so intense that neutrons themselves break down into a soup of quarks, a state of matter so exotic it defies our current physics. Wormholes could provide an escape valve for that energy, a hidden channel where particles or information bleed into other regions of the universe. It's a cosmic pressure release hidden in plain sight. The wildest possibility, these micro-wormholes might not just bridge distant points in our universe, they could tunnel into entirely different ones. The multiverse hypothesis, long a fringe idea, gets a surprising boost from neutron star physics. If spacetime is pinched tightly enough, it might temporarily puncture the barrier between universes, creating a fleeting connection to another reality with its own laws of physics. Imagine a neutron star as a cosmic vending machine, occasionally spitting out particles that don't quite belong to our universe, their properties subtly altered by the journey. Of course, proving any of this is a monumental challenge. Neutron stars are already fiendishly difficult to study, their interiors hidden behind impenetrable layers of ultra-dense matter. Any wormholes inside would be too small and unstable to detect directly, but subtle clues might linger. Gravitational waves from colliding neutron stars could carry faint echoes of internal structures, hints of spacetime anomalies that don't fit conventional models. Or perhaps certain particles emitted by neutron stars would bear the signature of having traversed a wormhole, their energy spectra just slightly off from what our physics predicts. What makes this theory so compelling isn't just the sci-fi imagery. It's the way it forces us to rethink the limits of matter and space. Neutron stars are already cosmic laboratories, pushing the boundaries of what's physically possible. If they're also hiding wormholes in their cores, then the universe's most destructive events, supernovas, might secretly be creators, weaving hidden threads through the fabric of reality itself. And that's a reminder that even in death, stars could be holding onto their greatest secrets, waiting for us to crack the code. At the smallest scales imaginable, far smaller than atoms, even tinier than quarks, spacetime might not be the smooth, unbroken fabric we picture. Instead, it could be a frothing, bubbling chaos known as quantum foam, where reality itself flickers in and out of existence. In this subatomic frenzy, wormholes aren't rare cosmic anomalies, they're everywhere, popping into being and vanishing in less time than it takes light to cross a proton. These aren't the grand interstellar tunnels of sci-fi, they're quantum-scale shortcuts, so tiny they'd make a neutron look like a galaxy. But here's the electrifying twist. Some theories suggest these fleeting wormholes could be stabilized, linked, or even woven into a vast, hidden network threading through the universe like invisible spider silk. The idea springs from quantum mechanics' wildest implications. At the Planck scale, the universe's smallest possible measurement energy fluctuations are so violent that spacetime itself becomes unstable. Imagine a pot of water at a rolling boil with bubbles constantly forming and bursting. Now replace the water with the fabric of reality, and those bubbles with microscopic wormholes. This isn't just poetic metaphor. Calculations by physicists like John Wheeler suggest that at these scales, spacetime's smoothness dissolves into a probabilistic frenzy, where wormholes and even entire baby universes blink in and out of existence. What if we could harness this quantum foam, theoretically stabilizing just one of these wormholes, prying it open with exotic matter or quantum energy, could create a doorway between distant points? But the real game changer is the possibility of a network. If these microscopic tunnels are as abundant as the math suggests, they might already be interconnected, a labyrinth of hidden passages woven into spacetime itself. Advanced civilizations, if they've mastered quantum engineering, might navigate this subatomic subway system, hopping between stars not by crossing space, but by diving into its tiniest cracks. The challenges, of course, are staggering. Quantum foam wormholes would be absurdly unstable, collapsing faster than we could detect them. Stabilizing them would require technology capable of manipulating spacetime at scales a billion times smaller than an atom, with energies rivaling the Big Bang. And even if we could, there's no guarantee these tunnels would lead anywhere useful. They might dump you into random points in space or time, or worse, into the heart of a star. Yet the theory refuses to fade because it solves two cosmic puzzles at once. First, it offers a potential mechanism for quantum entanglements, spooky action at a distance. Those linked particles might be whispering to each other through Planck-scale wormholes. Second, it hints that the universe's true architecture might be more like a sponge than a void, riddled with hidden tunnels we've yet to learn how to see. Perhaps the most tantalizing thought is this: if quantum foam wormholes exist, then the universe isn't just vast, it's layered. Behind the curtain of our everyday reality, an entire ecosystem of shortcuts might be humming unnoticed. And that changes everything. The cosmos we see through telescopes could be just the surface, with a hidden underworld of connections waiting to be mapped. All we need is the right lens or the courage to look closer than ever before. If our universe is just one bubble in an infinite cosmic foam of parallel realities, then wormholes might be the hidden threads stitching them together, cosmic backdoors between worlds where the laws of physics could be radically different. The idea isn't as far-fetched as it sounds. Modern theories like string theory and the inflationary multiverse suggest that our universe might be one of countless others, each born from separate big bangs or budding off from existing universes like branches on a tree. If that's true, then wormholes could be more than just shortcuts through space. They might be interdimensional gateways, tunnels where the very rules of reality shift as you travel from one end to the other. Picture a hallway with infinite doors, each leading to a universe where history played out slightly differently. One might have Earth where dinosaurs never went extinct. Another could have stars that burn blue instead of yellow, or gravity that's twice as strong. Wormholes linking these worlds wouldn't just defy distance, they'd defy logic, offering a glimpse into what might have been or what could still be. The math even allows for stranger possibilities, universes where time runs backward, or where entropy decreases instead of increases, making scrambled eggs spontaneously unscramble themselves. But here's where things get thorny. Crossing into another universe isn't like hopping between galaxies. The moment you step through a multiversal wormhole, you're playing by a new set of physical rules, ones that might not be compatible with your existence. The atoms in your body could unravel if the strong nuclear force is weaker there, or you might instantly freeze if the cosmic background temperature is lower. Even the act of observing another universe could destabilize the wormhole, snapping it shut like a book slamming closed. Some physicists speculate that these tunnels might be nature's way of recycling reality. Just as black holes might spawn new universes inside their singularities, wormholes could be birthing canals for cosmic inflation, funneling energy from one world to seed another. Others propose that multiversal wormholes are less like bridges and more like scars, leftover defects from when our universe peeled away from a neighboring one in the first fractions of a second after the Big Bang. The most tantalizing question isn't just whether these tunnels exist, but what they'd reveal about existence itself. If wormholes can connect alternate realities, then every choice you've ever made might still be playing out somewhere in some universe. The you that took that job overseas, the you that never met your best friend, they could all be real, separated only by a twist in spacetime we've yet to map. It's a humbling thought. The cosmos might not just be vast but endlessly varied, with wormholes as the ultimate proof that reality is far stranger than we ever dreamed. And if that's true, then the biggest mystery isn't how to build a wormhole, it's how to choose which door to open first. Negative mass sounds like something straight out of a physicist's thought experiment, but what if it's the missing ingredient for keeping wormholes open? Unlike exotic matter, which merely carries negative energy, negative mass would flip gravity's script entirely. Picture an object that doesn't just resist being pulled downward, but actively falls upward, repelled by ordinary matter like the same poles of a magnet. This isn't just theoretical whimsy. The equations of general relativity allow for such bizarre matter, and if it exists, it could be the ultimate stabilizer for interstellar shortcuts. Here's how it works. A wormhole's natural instinct is to collapse under its own gravitational pull. like a rubber band snapping back after being stretched. Exotic matter might prop it open by pushing outward, but negative mass would do something far more radical. It would invert the very forces trying to crush the tunnel. Imagine building a bridge where the supports don't just hold weight but actively repel the ground beneath them, creating a self-reinforcing structure. In wormhole terms, negative mass lining the throat could generate a gravitational repulsion strong enough to counteract the tunnel's tendency to implode, effectively making it self-sustaining. The catch: negative mass has never been observed, and its properties defy everyday intuition. If you pushed a negative mass object, it would accelerate toward you instead of away, as if the universe got its physics backward. Some speculative theories suggest it might exist in the quantum foam or as a peculiar side effect of dark energy, but for now, it's a ghost in the math. Yet the implications are too tantalizing to ignore. A wormhole stabilized by negative mass wouldn't just stay open, it might require no ongoing energy input, functioning like a cosmic elevator that never needs maintenance. Even stranger, negative mass could solve one of the biggest headaches in wormhole engineering: time dilation. Ordinarily, the intense gravity near a wormhole's entrance would slow time to a crawl for travelers relative to the outside universe. But negative mass's repulsive gravity might cancel this effect, sinking clocks on both ends of the tunnel. Suddenly, a trip through a wormhole wouldn't just bridge space, it could keep you perfectly in sync with the timeline you left behind. No interstellar jet lag required. Of course, the skeptics have plenty of ammunition. Negative mass raises thorny questions about causality and energy conservation. Could it create perpetual motion machines or violate the laws of thermodynamics? The math is still fuzzy, and some physicists argue that even if negative mass exists, nature might prevent it from being harnessed this way. But that's the beauty of frontier science. Every unanswered question is a doorway to a deeper mystery. What makes this theory so compelling isn't just the engineering potential. It's the audacity of the premise that the universe might harbor matter so alien, it rewrites the rules of motion, gravity, and time itself. And if we ever found or synthesized it, the dream of stepping through a wormhole wouldn't just be possible, it might be as straightforward as walking through a door. What if the universe isn't just expanding? It's computing. This is the mind-bending premise behind the idea that wormholes could be nature's version of quantum processors, crunching data at scales so vast they make our fastest supercomputers look like abacuses. The theory hinges on a startling parallel. Just as entangled particles seem to share information instantly across any distance, wormholes might function as spacetime's hardware, executing calculations by linking distant points in the cosmos through hidden shortcuts. Imagine a cosmic internet where the cables aren't fiber optic lines but warps in the fabric of reality itself. A network where information doesn't travel but simply appears where it's needed, as if the universe had already solved the equation before we even asked the question. The spark for this idea comes from an unexpected marriage of black hole physics and quantum mechanics. Black holes, it turns out, might not destroy information but scramble and preserve it on their event horizons, a phenomenon known as the holographic principle. Now take that concept and stretch it further. If a black hole's surface can encode information like a hard drive, then a wormhole, a bridge between such surfaces, could theoretically transfer that data without delay. It's as if the universe has built-in error correction, ensuring no information ever gets lost, just redistributed through spacetime's hidden back alleys. But here's where it gets even wilder. Quantum computers rely on qubits that can exist in multiple states at once, solving problems exponentially faster than classical bits. Wormholes, some physicists suggest, might exploit a similar principle. Their ability to connect distant regions instantaneously mirrors quantum entanglements, spooky action at a distance, hinting that the universe's underlying code could be running on wormhole-like connections we've yet to fully decipher. Picture a galaxy-spanning processor where every star, planet, and atom is a node in the computation, with wormholes threading them together into a single, inseparable whole. The implications are staggering. If true, it would mean the cosmos isn't just governed by physical laws, it's enacting them, calculating its own evolution in real time. Dark energy's accelerating expansion. Maybe the universe is allocating more memory. Black holes, they could be data compression hubs. Even our perception of time might be a side effect of this cosmic computation, with each moment a new frame rendered by the universe's hidden circuitry. Of course, proving any of this is a monumental challenge. We'd need to detect signatures of information processing in phenomena like gravitational waves or quantum fluctuations, subtle patterns that betray the universe's computational handiwork. Some researchers are already looking, scouring the cosmic microwave background for anomalies that might resemble error codes in spacetime's firmware. Others propose that advanced civilizations might have learned to hijack these natural processes, using wormholes as substrates for their own unfathomable calculations. What makes this theory so electrifying isn't just the techno-cosmic imagery. It's the way it reframes existence itself. If wormholes are quantum computers, then reality isn't just something we observe, it's something we're embedded in, like characters inside a simulation we're only beginning to debug. And that raises a humbling question. If the universe is crunching numbers, what's it solving for? The answer might be written in the very wormholes we're trying to understand. The Fermi Paradox asks a haunting question. If the universe is teeming with potential for life, where are all the aliens? Wormholes might hold a startling answer. Imagine a galaxy crisscrossed with invisible highways, where advanced civilizations zip between stars undetected, their comings and goings hidden in the folds of spacetime. They wouldn't need to colonize every planet or broadcast signals across the void if they've mastered cosmic shortcuts. To them, Earth might be a quiet backwater, a rest stop they've quietly bypassed for millennia. But there's a darker twist. Wormholes could explain the eerie silence in another way by making interstellar travel too dangerous to risk. Picture a universe littered with unstable wormholes, their entrances disguised as black holes or cosmic anomalies. Any civilization bold enough to attempt traversal might vanish without a trace, swallowed by tunnels that collapse mid-journey or dump travelers into lethal regions of spacetime. The Great Filter, the hypothetical barrier preventing life from spreading across the galaxy, might not be a cosmic catastrophe. It could be the wormholes themselves, offering the illusion of Chinese letter while hiding fatal pitfalls. Then again, maybe we're the ones missing the clues. Wormholes might not look the way we expect. Advanced aliens could have engineered them to emit no detectable radiation, masking their presence by bending light and gravity around them like cosmic stealth technology. Or perhaps they're leveraging higher dimensions, their wormholes existing just outside our perceptual reach. It's like ants searching for airplanes. The scale and nature of the technology might be so far beyond us, we wouldn't recognize it even if it were right overhead. The most tantalizing possibility, wormholes could render traditional space travel obsolete. A civilization that cracks the code of stable wormholes wouldn't need slow, visible starships. They'd leave no exhaust trails, no debris, no radio chatter, just fleeting gravitational ripples or quantum anomalies we've yet to learn how to measure. Our current searches for extraterrestrial intelligence focus on electromagnetic signals, but what if the real evidence is written in the subtle warping of spacetime itself? This theory doesn't just reshape the Fermi Paradox, it turns it inside out. The absence of aliens might not mean we're alone. It could mean we're surrounded by civilizations moving through a hidden layer of reality, their presence as undetectable to us as radio waves would be to medieval farmers. The universe's greatest secret might not be the silence, but the shortcuts humming just beneath the surface, waiting for us to learn how to listen. At the heart of every star, in the searing fury of a fusion reactor, or even inside the world's most powerful particle accelerators, matter doesn't behave like anything we encounter in daily life. It becomes plasma, a fourth state of matter so energetic that electrons tear free from atoms, creating a swirling soup of charged particles. But hidden within this chaos, physicists are uncovering something extraordinary, the same extreme conditions that might one day unlock the secrets of wormholes. Plasma isn't just hot gas, it's a universe in miniature, governed by forces so intense they warp the rules of physics. In the cores of stars, magnetic fields twist plasma into braids of energy, creating structures that eerily resemble the theoretical models of wormhole throats. When particles in these plasmas collide at near-light speeds, they generate fleeting distortions in space-time, tiny echoes of the warping needed to stitch together cosmic shortcuts. It's as if nature is teasing us with hints, showing us wormhole-like behavior in environments we can actually study here on Earth. The key lies in plasma's unique ability to self-organize under extreme conditions. Take tokamaks, the donut-shaped reactors designed to harness fusion energy. Inside these devices, plasma swirls in precise, self-sustaining rings, a dance of particles and magnetic fields that some physicists suspect could mimic the stabilization of a wormhole's throat. If exotic matter is the glue holding wormholes open, then plasma might be the closest analog we have, with its ability to generate regions of negative pressure and bizarre quantum effects under the right conditions. Even more tantalizing are the parallels between plasma turbulence and the quantum foam of spacetime. At scales smaller than atoms, spacetime is thought to froth with virtual particles popping in and out of existence, a chaos not unlike the unpredictable eddies of high-energy plasma. Some researchers speculate that by mastering plasma's turbulence, we might stumble onto techniques to manipulate spacetime's own micro-instabilities, coaxing them into stable wormholes. It's a long shot, but the overlap is too compelling to ignore. The most promising experiments are already underway. In labs like the Large Hadron Collider, physicists slam particles together with enough energy to briefly recreate conditions not seen since the Big Bang. These collisions don't just produce new particles, they twist spacetime itself into knots, creating microscopic environments where the fabric of reality might momentarily pinch into wormhole-like structures. While we can't yet detect these fleeting phenomena directly, the math suggests they're there, hiding in the data like cosmic fingerprints. What makes this theory so revolutionary isn't just the potential for discovery, it's the shift in perspective. Instead of staring at the cosmos hoping to spot a wormhole, we might be able to engineer their conditions in a lab, unraveling the physics piece by piece in environments we control. Plasma could be the Rosetta Stone that translates the language of wormholes from abstract equations into tangible experiments. And if we succeed, the dream of interstellar shortcuts might not require a black hole or exotic matter, just the mastery of the universe's most abundant and energetic state of matter, right here at home. What if traversing a wormhole doesn't require a spaceship or even a physical body, just the power of thought? This is the radical proposition at the heart of some fringe theories, linking consciousness directly to the fabric of spacetime. The idea sounds like pure mysticism, but it emerges from a surprising intersection of quantum physics and neuroscience, where the observer's mind isn't just a passive spectator but an active participant in shaping reality. Imagine consciousness as a tuning fork, resonating with the vibrations of a wormhole structure, aligning mental states across vast distances or even different timelines. It's a concept that blurs the line between science and philosophy, suggesting that the universe's greatest shortcuts might not be found in the stars, but within us. The spark for this theory comes from quantum mechanics' most perplexing feature, the observer effect, where the act of measurement seems to influence the behavior of particles. If consciousness can collapse quantum probabilities into definite states, could it also interact with spacetime's geometry on a larger scale? Some researchers speculate that highly focused mental states, like those achieved in deep meditation or altered consciousness, might momentarily synchronize with the quantum fluctuations inside a wormhole, creating a bridge between mind and cosmos. Think of it like a radio dial. If consciousness operates at certain frequencies, tuning into the right one might allow a form of non-local awareness where perception transcends physical location. But the implications go even further. If consciousness can interface with wormholes, then time travel might not require machines at all. Ancient traditions and modern psychedelic experiences alike describe visions of distant eras or alien landscapes. Could these be glimpses of actual spacetime coordinates accessed through mental wormholes? The idea finds eerie parallels in accounts of remote viewing, where individuals claim to perceive distant locations with uncanny accuracy, as if their awareness briefly slipped through a crack in reality's facade. Skeptics dismiss this as fantasy, yet the math of quantum entanglement, where particles remain connected across space, hints that information might bypass conventional limits in ways we don't yet understand. The most tantalizing and controversial twist: consciousness might not just use wormholes, it could help create them. Theories like orchestrated objective reduction suggest that quantum processes in the brain's microtubules could generate tiny spacetime distortions, weaving microscopic wormholes that facilitate intuitive leaps or creative insight. It's a wild notion, but not without precedent. Near-death experiences often include reports of traversing tunnels toward other realms, while advanced meditators describe sensations of dissolving into interconnectedness. Could these subjective experiences reflect an unconscious navigation of spacetime's hidden architecture? Of course, the hurdles are enormous. No experiment has ever proven a direct link between consciousness and wormholes, and mainstream physics remains deeply skeptical. But the questions linger, haunting the edges of science. If the universe is fundamentally participatory, if mind and matter are entangled at the deepest level, then the greatest journeys might not be through space, but into the untapped potentials of awareness itself. And that's a frontier no spacecraft could ever reach. The universe thrives on cycle. Stars are born from cosmic dust, blaze for eons, then scatter their remains to seed new generations. But what if wormholes are the invisible conveyor belts in this grand recycling system? Picture a dying star collapsing into a black hole, its matter compressed beyond recognition. Instead of vanishing forever, that material might get shunted through a hidden tunnel, reappearing light years away as the building blocks of a fledgling galaxy. It's a cosmic ecosystem where nothing truly dies. It just gets repurposed through spacetime's back channels. This idea isn't as whimsical as it sounds. The math of general relativity allows for wormholes to act as drains and faucets, siphoning energy from one region of the universe and depositing it elsewhere. Imagine a supernova's explosive debris not just expanding outward but funneled through a wormhole's throat, emerging near a stellar nursery where gravity sculpts it into new stars and planets. The universe wouldn't need to create matter from scratch. It could redistribute what already exists, like a gardener composting fallen leaves to nourish next season's growth. The implications rewrite how we view cosmic evolution. galaxies separated by vast distances might share material through these hidden pipelines, explaining oddities like stars with anomalous chemical compositions or rogue planets drifting between stars. Some astronomers speculate that certain empty regions of space voids where matter seems suspiciously scarce could actually be wormhole dumping grounds, areas where recycled material accumulates before being drawn into new structures. It's as if the cosmos has its own supply chain, with wormholes as the delivery trucks operating on routes we can't yet map. But here's the catch: evidence for this recycling would be subtle. Wormholes wouldn't leave shipping labels on the matter they transport. Instead, scientists hunt for statistical anomalies, patterns of element distribution that don't fit standard models of stellar life cycles. For instance, pockets of heavy metals like gold or platinum might cluster in ways that suggest they didn't originate locally, but were transplanted from distant supernova. Gravitational wave observatories could also play a role, listening for the faint echoes of wormholes snapping shut after transferring matter, like cosmic elevator doors closing behind an unseen delivery. The most poetic possibility: this process might not be random. Wormholes could act as cosmic stabilizers, venting excess energy from overcrowded regions to fuel sparse ones, maintaining equilibrium on a scale we're only beginning to fathom. In this view, the universe isn't just expanding, it's breathing, with wormholes as the capillaries distributing its lifeblood. And if that's true, then every atom in our bodies might have taken a shortcut through spacetime to get here, making us all veterans of journeys we'll never remember. Gravitational waves, the faint ripples in spacetime first detected in 2015, have already revolutionized our understanding of black holes and neutron stars. But hidden within those cosmic tremors might be something even more extraordinary: whispers of wormholes. When LIGO picked up the distant chirps of colliding black holes, it wasn't just listening to the death throes of massive objects, it was tuning into the very fabric of reality, vibrating like a drum. Now, physicists are asking a daring question: could future gravitational wave observatories catch the subtler echoes of a wormhole snapping shut, or two exotic objects spiraling toward each other through a hidden tunnel? The key lies in the unique fingerprints wormholes would leave in spacetime. Unlike black holes, which produce clean, predictable wave patterns when they merge, wormholes could distort gravitational waves in bizarre ways. Picture two massive objects orbiting each other. Through a wormhole's throat, their gravitational waves would arrive at Earth with strange delays or repetitions, like an echo in a cathedral. Some models even suggest that wormholes might produce anti-chirps, where the frequency of the waves rises instead of falling as objects approach each other, defying conventional expectations. These anomalies would stand out like wrong notes in a symphony, alerting scientists to something profoundly unusual at play. Next-generation detectors like LISA, a space-based gravitational wave observatory set to launch in the 2030s, could be the game changers. Freed from Earth's seismic noise, LISA million-kilometer arms will sense waves 1,000 times weaker than LIGO can detect, potentially picking up the faint tremors of microscopic wormholes or ancient cosmic strings vibrating like plucked guitar strings. Even more tantalizing are proposals to combine gravitational wave data with neutrino or gamma-ray observations, a cosmic triangulation that might catch a wormhole's secondary effects, like bursts of particles ejected from its far end. But the real prize would be catching a wormhole in the act of forming or collapsing. Theoretically, this event would release a gravitational wave burst, a sharp, asymmetric spike, unlike the smooth mergers we've seen so far. Some physicists speculate that certain unexplained glitches in existing LIGO data could be the first hints of these elusive phenomena, buried under noise like a faint radio signal struggling to break through static. Future AI-powered analysis might sift through decades of data, hunting for patterns that human eyes would miss. What makes this search so electrifying isn't just the prospect of discovery, it's the way gravitational waves could reveal wormholes without us ever seeing them directly. Like listening to the wind howl through a canyon and deducing the shape of the rocks, we might map spacetime's hidden tunnels through their echoes alone. And if we succeed, the universe's greatest shortcuts could finally step out of theory and into reality. What if the closest we ever get to traversing a wormhole isn't in a spacecraft, but inside a virtual universe of our own creation? While physicists grapple with the monumental challenges of stabilizing real wormholes, a parallel revolution is unfolding in the realm of virtual reality, one that might let us cheat the cosmos and experience interstellar shortcuts decades before they're physically possible. Imagine slipping on a headset and feeling the gut-wrenching twist of spacetime folding around you, watching stars streak past as you plunge through a tunnel of warped light, emerging seconds later in a distant galaxy, all from the safety of your living room. This isn't just entertainment, it's a sandbox for testing theories, training future astronauts, and rewiring our brains to comprehend the incomprehensible. The key lies in the explosive advances in VR technology and computational physics. Modern simulations can already recreate black holes with startling accuracy, using Einstein's equations to render their gravitational lensing and time dilation effects in real time. Now, researchers are pushing further, programming wormhole analogs that behave according to the latest theoretical models. These virtual wormholes aren't just pretty visuals, they're interactive laboratories where users can manipulate variables like exotic matter density or throat curvature, observing how changes ripple through the simulated spacetime. It's like having a universe-building toolkit where the laws of physics are sliders you adjust with a flick of your wrist. But the true breakthrough isn't just in the tech, it's in the human mind. Navigating a wormhole, even virtually, requires our brains to process distortions of space and time that defy everyday intuition. Pilots and astronauts train for years to adapt to the disorientation of zero gravity or high G-forces. VR wormholes could serve as a similar training ground for the mind-bending perceptions of relativistic travel. Early experiments show that repeated exposure to simulated warp effects can reduce spatial disorientation, priming neural pathways to handle the real thing. Think of it as cosmic motion sickness therapy, preparing explorers for the day when stepping through a wormhole might mean confronting a sky where stars aren't where they're supposed to be. The implications ripple beyond education. Virtual wormholes could democratize interstellar curiosity, letting anyone, not just physicists or billionaires, experience the thrill of cosmic shortcuts. Artists and storytellers are already collaborating with scientists to craft immersive narratives where wormholes aren't just plot devices but fully realized environments, complete with realistic physics and speculative ecosystems on the other side. These experiences aren't just fun, they're reshaping public perception of space travel, turning abstract concepts into visceral, emotional journeys that inspire the next generation of explorers. Yet the most tantalizing possibility is how VR might accelerate real-world breakthroughs. Simulated wormholes allow researchers to test what-if scenarios too risky or expensive to attempt physically. What happens if you send a pulse of gamma rays through a spinning wormhole? Can quantum entanglement effects stabilize the tunnel? These questions can be probed in minutes inside a simulation, generating hypotheses that guide real experiments. It's a feedback loop between the virtual and the physical, a dance of imagination and discovery where each informs the other. Of course, no simulation can perfectly replicate the infinite complexity of real spacetime. The quantum foam, the tug of dark matter, the whispers of higher dimensions, these nuances remain beyond our computational reach for now. But every iteration brings us closer, blurring the line between model and reality. And that raises a provocative thought. If we one day build a working wormhole, will it feel as familiar as the simulations we've lived inside for years? The answer might lie not in the stars, but in the headsets we're already strapping on, teaching our minds to reach across the cosmos before our bodies ever get the chance. Time has always been the universe's strictest one-way street until wormholes crashed the party with a radical proposition. What if the arrow of time isn't as unshakable as we think? We've been conditioned to see time as an unstoppable river flowing from past to future, but wormholes introduce a twist. They could bend that river into a loop where cause and effect start playing by new rules. Picture a tunnel where entering one end sends you backward in time while the other spits you into the future, like stepping onto an escalator that moves in both directions simultaneously. This isn't just a sci-fi trope. The math of general relativity allows for it, revealing a shocking truth. Wormholes don't just warp space, they tangle time itself into knots. The mystery starts with entropy, the universe's built-in tendency toward disorder. It's why ice melts in your drink but never spontaneously refreezes, why we remember the past but not the future. Wormholes threaten to upend this cosmic rulebook. In certain configurations, they could create closed time-like curves, paths where time circles back on itself, allowing events to become their own causes. Imagine tossing a ball through a wormhole only to watch it fly out and hit its past self midair, a paradox made real. Theoretical models suggest that exotic matter stabilizing the wormhole's throat might also enforce a kind of temporal traffic control, preventing such paradoxes by rerouting causality like a cosmic roundabout. But the implications are still dizzying. Here's where it gets even stranger. Quantum mechanics hints that time's arrow might be more fluid than we realize. At the smallest scales, particles don't seem to care about moving forward or backward. Wormholes could amplify these quantum quirks to macroscopic scales, creating environments where entropy runs backward locally. Picture a wormhole's interior where shattered glass reassembles itself or smoke pours back into a cigarette. These reversals wouldn't violate the universe's overall march toward disorder. They'd just carve out temporary pockets where time's rules flip like a flipped hourglass. Yet the most profound clue lies in black holes. When matter crosses a black hole's event horizon from our perspective, time for that object appears to freeze. But what if it's not stopping? What if it's being redirected? Wormholes linked to black holes might act as cosmic spillways, channeling that lost time into another region of spacetime. In this view, the arrow of time isn't disappearing. It's being woven into the fabric of the universe elsewhere, like a river diverted underground. This could explain why time seems to flow at all, not as a fundamental property, but as an emergent feature of how spacetime's hidden tunnels redistribute cause and effect. The stakes couldn't be higher. If wormholes can manipulate time's flow, they might hold the key to unifying relativity and quantum mechanics, the holy grail of modern physics. They'd force us to ask whether time is a true dimension or just a byproduct of deeper, wormhole-like connections between events. Every paradox they conjure isn't a flaw in the theory, it's a flashlight illuminating the cracks in our understanding. And that's the real revelation. Wormholes aren't just challenging time's arrow, they're offering us a chisel to break it open and see what's inside. The idea of wormholes as cosmic shortcuts is thrilling, but what if they're more than just interstellar highways? Hidden within their twisted space-time could lie the ultimate power source, a reservoir of energy so vast it could fuel civilizations for millennia. Picture the throat of a wormhole where gravitational forces stretch space to its breaking point. The tidal energies there don't just bend reality, they churn it into a maelstrom of potential, like a dynamo spinning at the heart of creation itself. For a society advanced enough to withstand the extremes, tapping that energy could be the key to unlocking the stars. Think of it like harnessing a black hole's spin, but with a crucial advantage: wormholes, if stabilized, offer access to both ends of the tunnel. Imagine dropping a generator near one mouth where the gravitational shear creates intense differential forces, then collecting the output at the other end. The energy isn't just local, it's transmissible across light years in an instant, a power grid woven through spacetime itself. Some models suggest that the Casimir effect, those fleeting quantum fluctuations that hint at negative energy, could be amplified near a wormhole's throat, creating a feedback loop where vacuum energy is extracted and stabilized. It's like plugging into the universe's own battery, drawing from the raw tension of stretched spacetime. The engineering challenges, of course, are staggering. Any device near a wormhole's throat would need to withstand gravitational tides strong enough to shred planets, not to resist the torrents of high-energy particles likely funneled through the tunnel. But advanced civilizations might not need physical machinery at all. Magnetic fields projected around the wormhole could act as invisible turbines, converting spacetime's curvature into usable energy like a windmill catches the breeze. Or perhaps they'd exploit the wormhole's natural Hawking radiation, the faint glow emitted by relativistic structures, capturing it with solar sail, like collectors tuned to absorb quantum emissions. The most audacious possibility: wormholes might not just store energy, they could generate it. If exotic matter or negative mass truly stabilizes these tunnels, their repulsive gravity could be weaponized into a cosmic perpetuum mobile, a self-sustaining engine where the act of holding the wormhole open releases more energy than it consumes. It's the holy grail of physics, a system that defies entropy, not by breaking the laws of thermodynamics, but by bending them over the knee of relativity. Yet the implications go beyond mere power. A civilization that masters wormhole energy wouldn't just light its cities, it could reshape galaxies, need to move a star. Use the wormhole's gravity like a tow cable, want to cool a dying sun, siphon its heat into a wormhole's mouth, dispersing it harmlessly across the cosmos. The universe's greatest forces tamed not with brute strength, but with the precision of a locksmith turning spacetime's key. Of course, we're millennia away from such feats. But the theories are already scribbled in the margins of relativity's equations, waiting for a species bold enough to test them. And that's the real promise of wormholes, not just where they might take us, but what they might teach us about the energy humming in the fabric of existence itself. DNA is often called the blueprint of life, but what if it's also a blueprint for something far grander, a biological wormhole? This might sound like the plot of a sci-fi novel, but a handful of radical theories propose that the double helix in every cell of your body could share uncanny similarities with the structure of spacetime's most elusive shortcuts. At first glance, the idea seems absurd. How could a molecule that fits inside a microscopic cell have anything to do with cosmic tunnels spanning light years? The answer might lie not in size, but in function. Just as DNA transmits genetic information across generations, wormholes could transmit matter and energy across the universe, both acting as conduits for something fundamental, whether it's biological data or the fabric of reality itself. The spark for this wild connection comes from an unexpected place: quantum biology. Scientists have long known that DNA operates with eerie efficiency, almost as if it's leveraging quantum effects to store and transmit information. Some experiments even suggest that electrons in DNA might exhibit quantum coherence, meaning they can exist in multiple states at once, much like particles entangled across cosmic distances. Now stretch that idea further. If quantum entanglement, often linked to wormhole physics, plays a role in how DNA functions, could the molecule itself be a microcosm of spacetime's hidden architecture? Imagine each twist of the double helix as a fractal echo of a wormhole spiraling throat, both structures optimized for moving information through folds in their respective landscapes. But the parallels don't stop there. DNA isn't just a passive repository, it's dynamic, capable of repairing itself and adapting to environmental changes. Wormholes in some models might share this self-correcting quality. Exotic matter or quantum fields stabilizing a wormhole could behave like molecular enzymes, constantly adjusting to keep the tunnel open against gravitational collapse. It's as if nature stumbled upon a universal design principle, whether crafting life or stitching spacetime. The same strategies for resilience and transmission keep appearing, just at vastly different scales. The most provocative version of this theory comes from fringe biophysics, where researchers speculate that DNA might not just resemble a wormhole, it could actively create one. In certain extreme conditions, like the intense electromagnetic fields near a black hole or the heart of a high-energy lab experiment, the molecule's structure might warp spacetime around it, generating fleeting micro-wormholes. These wouldn't be tunnels you could step through, but perhaps channels for quantum information, linking biological systems instantaneously across distances. It's a stretch, but not entirely implausible. After all, if bacteria can harness quantum tunneling for photosynthesis, why couldn't evolution stumble upon spacetime tunneling too? Skeptics, of course, have plenty of ammunition. DNA operates in the warm, messy environment of a cell, far from the ultra-cold, ultra-precise conditions where quantum effects usually thrive. And while wormholes are hypothetical, DNA is undeniably real, comparing the two risks, conflating metaphor with mechanism. Yet the theory lingers because it taps into a deeper question: is life itself a kind of spacetime anomaly? If the universe tends toward entropy and disorder, life defiantly builds complexity. Wormholes, in their defiance of conventional physics, might be cosmic kin to biology's stubborn insistence on order. Whether DNA holds the key to wormholes or not, the idea forces us to rethink the boundaries between life and the cosmos. After all, every atom in our bodies was forged in the hearts of stars. We're already made of stardust threaded through with spacetime's secrets. Maybe the connection runs deeper than we ever imagined. Long before physicists scribbled equations about spacetime tunnels, storytellers were dreaming of doorways to distant worlds. Wormholes have always been more than a scientific curiosity. They're a mirror reflecting humanity's deepest yearnings to transcend limits. Take the ancient Greeks, who imagined the oracle at Delphi as a literal portal to divine knowledge, or Norse myths of the Bifrost, a shimmering bridge linking realms. These weren't just fanciful tales, they were early attempts to grapple with the same question driving modern astrophysics. What if the boundaries we take for granted aren't fixed at all? Fast forward to the 20th century, and wormholes exploded into pop culture with a fervor that often outpaced the science. The iconic Stargate from 2001, A Space Odyssey, wasn't just a psychedelic light show. It was Kubrick's vision of a cosmic shortcut, a visual metaphor for evolution leaping across spacetime. Then came Contact, where Jodie Foster's journey through a wormhole machine blended rigorous science with spine-tingling wonder, thanks to Carl Sagan's insistence on consulting physicists like Kip Thorne. But it was Interstellar that changed the game. Thorne's equations literally rendered the film's wormhole as a shimmering sphere, bending starlight with Hollywood's first scientifically accurate depiction. The irony, those breathtaking visuals led to real academic papers, proving art and science aren't just neighbors, they're collaborators. What's fascinating is how these portrayals shape public perception. For many, wormholes aren't abstract math problems but visceral experiences. Remember the gut-drop moment when the Event Horizon ship's crew faced a hellish dimension, or the bittersweet awe of Interstellar's Tesseract, where love became a tangible force. These stories embed wormholes in our collective psyche, making the improbable feel intimate. Even video games like Portal weaponized wormhole physics, turning space-time puzzles into playgrounds where players internalized concepts like non-Euclidean geometry without cracking a textbook. Yet the most profound impact might be on the scientists themselves. Cosmologist Sean Carroll has admitted that Star Trek fueled his childhood fascination with physics, while Michio Kaku credits comic books for sparking his interest in higher dimensions. It's a virtuous cycle. Science inspires art, which then inspires new generations of scientists to push boundaries further. Today, projects like the Culture novels and Arrival's linguistic wormholes explore not just the how of space-time travel, but the why, probing how crossing cosmic thresholds might redefine what it means to be human. Perhaps that's the real magic of wormholes in culture. They're not just plot devices but vessels for our oldest questions. Are we alone? What lies beyond? Can we outrun time? Whether etched on cave walls or rendered in IMAX, these stories remind us that the universe's greatest mysteries belong to everyone, not just those who speak the language of equations. And sometimes it's the dreamers who sketch the map before the explorers find the path. The Big Bang wasn't just the beginning of time. It was a cosmic pressure cooker where the laws of physics as we know them were forged in fire. And in that primordial inferno, space-time itself might have been stretched, twisted, and punctured like molten glass, leaving behind scars in the form of wormholes. These wouldn't be the carefully engineered tunnels of far future civilizations, but raw, ragged passages born from the universe's violent infancy. Picture the aftermath of a stormy sea, where turbulent waves leave behind frothy bubbles in their wake. Now imagine those bubbles are space-time defects, frozen into the fabric of reality as it cooled wormholes that could still linger today, hidden in the cosmic background like ancient ruins. The math behind this idea is as elegant as it is mind-bending. In the first fractions of a second after the Big Bang, the universe underwent a phase called inflation, expanding faster than the speed of light. This explosive growth wasn't perfectly smooth. Quantum fluctuations created tiny ripples in spacetime, some of which might have pinched into microscopic wormholes. Unlike black holes, which form from collapsing stars, these primordial wormholes would be woven into the universe's very structure, relics of a time when gravity and quantum forces were indistinguishable. Some theories even suggest they could be threaded with cosmic strings, ultra-dense filaments left over from the early universe, acting as scaffolding to keep them from collapsing. But why haven't we spotted these ancient tunnels? The answer might lie in their size. Primordial wormholes could be vanishingly small, far tinier than an atom, making them nearly impossible to detect with current technology. Yet their influence could be everywhere. If they exist, they might subtly warp the cosmic microwave background, the afterglow of the Big Bang, leaving faint imprints like fingerprints on glass. Others speculate they could act as seeds for dark matter, clustering invisible particles around their throats like spiders weaving webs, the most tantalizing possibility. Some might have grown with the expanding universe, stretching from microscopic quirks to macroscopic bridges over billions of years. The wildest twist comes from multiverse theories. If our universe is one bubble in a vast cosmic foam, primordial wormholes could be the tendrils connecting us to neighboring universes, frozen in place as inflation slammed the door on their growth. These wouldn't be traversable tunnels, more like scars where realities once touched. Yet their presence could explain anomalies in the universe's large-scale structure. like unexplained voids or peculiar gravitational lensing where spacetime bends in ways that defy conventional models. What makes this theory so compelling isn't just the science, it's the poetry. If primordial wormholes exist, they're cosmic time capsules holding secrets from the universe's first moments. Studying them wouldn't just reveal how spacetime bends, it could unlock how spacetime was born. And that's a reminder that the universe's greatest mysteries might not lie in the distant future, but in the echoes of its explosive past waiting for us to listen. At first glance, wormholes seem to throw a cosmic wrench into Einstein's sacred rule: nothing can travel faster than light. If you can step through a tunnel in space-time and emerge light years away in an instant, haven't you just shattered relativity's speed limit? Not so fast. The genius of wormholes isn't that they break the rules, it's that they rewrite the game entirely. Here's the twist: relativity doesn't forbid objects from reaching distant locations faster than light could traverse the space between them. It forbids objects from accelerating through space past light speed. Wormholes cleverly sidestep this by bending the arena itself. Imagine two cities on opposite sides of a mountain. Driving between them at legal speeds would take hours, but a tunnel through the mountain lets you arrive in minutes without ever exceeding the speed limit. Wormholes work the same way. They don't propel you faster than light. They erase the distance you'd need to cross. The light speed limit stays intact because you're not moving through space at all. You're taking a detour through spacetime's back alleys, but the plot thickens when we consider causality, the bedrock principle that cause must precede effect. If wormholes link not just space but time, could they create scenarios where a message arrives before it's sent? Relativity allows for this mathematically, but physicists suspect nature has safeguards. Quantum mechanics hints that vacuum fluctuations near a wormhole's throat might generate chaotic feedback, collapsing the tunnel before paradoxes occur. It's as if the universe has built-in circuit breakers, tripping the moment causality threatens to short-circuit. The real magic lies in the geometry. A stable wormhole's throat acts like a cosmic elevator shaft, with spacetime's curvature doing the heavy lifting. Light racing through normal space is still the universe's fastest sprinter, but wormholes change the track, letting you cheat without disqualification. Future civilizations might not break the light barrier. They'll just redraw the map, proving once again that in physics, the most revolutionary solutions aren't about breaking rules, but understanding them deeper than anyone thought possible. Picture a world where stepping onto a wormhole platform is as routine as boarding a subway. No more years-long voyages to Mars, no generational ships straining under the weight of supplies, just a brief walk through a shimmering portal, and you're standing on the red sands of another world. This isn't just about faster travel, it's about rewriting the very concept of distance. Cities could sprawl across multiple planets, their neighborhoods linked by wormhole, commutes as seamlessly as bridges connect islands. The morning rush hour might include streams of workers stepping through portals to off-world offices, while families share dinners across planets, their tables set under alien skies one moment and Earth's familiar glow the next. The economic implications would dwarf every industrial revolution combined. Mining asteroids for rare metals becomes trivial when you can transport entire ore deposits instantaneously. Energy shortages could vanish as fusion reactors tap the furious cores of stars, their power beamed through wormhole conduits to light up distant colonies. Entire industries would rise around wormhole maintenance, exotic matter harvesting, and interstellar tourism, while others, like traditional shipping or fossil fuels, fade into obsolescence. The global economy wouldn't just grow, it would fractalize, with supply chains spanning solar systems and markets fluctuating based on discoveries in galaxies we've yet to name. But the true revolution would be cultural. Wormholes wouldn't just move bodies, they'd dissolve barriers between civilizations. Imagine artists on Titan collaborating with musicians in a Proxima Centauri metropolis, blending aesthetics evolved under different suns. Universities might host campuses where students study Martian geology in the morning and swim in Europa's subsurface oceans by afternoon. Religions, philosophies, and political systems would cross-pollinate at light speed, forcing humanity to confront its differences not as divisions, but as facets of a sprawling, interconnected identity. Yet this future isn't without shadows. Wormhole access could become the ultimate inequality divider, with only the wealthy owning portals to paradise worlds while the rest remain earthbound. Colonial disputes might escalate into wars over who controls the exits of key wormholes, turning cosmic shortcuts into strategic choke points. And what happens if a wormhole collapses mid-transit, or worse, drops a colony into the path of an undetected gamma-ray burst? The same technology that unites could also amplify catastrophes, linking disasters across light years like dominoes. Perhaps most profoundly, wormholes would force us to redefine home. With a cosmos reduced to a neighborhood, would Earth remain humanity's cradle, or just one address among many? Would we cling to our pale blue dot, or dissolve into the stars, our descendants becoming a species unmoored from any single world? The answer might lie in the choices we make long before the first wormhole stabilizes, whether we build these bridges to escape, to explore, or to finally outgrow the tribal instincts that have defined us for millennia. One thing is certain, mastering wormholes wouldn't just change where we live, it would change what it means to be human, and that transformation, not the technology itself, might be the greatest journey of all. What if the ultimate secret of wormholes isn't buried in the equations of general relativity, but in the lines of code running a cosmic simulation? This is the mind-bending premise of the simulation hypothesis. The idea that our universe isn't the base layer of reality, but an intricate construct built by some advanced civilization. And if that's true, wormholes might not be natural phenomena at all. They could be deliberate backdoors left in the cosmic software like cheat codes in a video game, waiting for players savvy enough to find them. Think about how glitches work in virtual worlds. Sometimes a programmer's oversight lets players clip through walls or teleport to hidden areas. Wormholes could be the universe's equivalent, a glitch in spacetime's rendering engine that skips the usual distance calculations. Imagine the creators of our simulation embedding these shortcuts as Easter eggs, either to test our ingenuity or to provide emergency exits for debugging. It's a radical thought, but not without precedent. Even in our own rudimentary simulations like climate models or video games, developers build in shortcuts to navigate vast datasets or skip ahead to key events. Why wouldn't a universe-scale simulation have similar tools? The implications ripple through physics and philosophy alike. If wormholes are programmable features, their bizarre properties start to make eerie sense. Exotic matter with negative energy that could just be an override in the simulation's gravity parameters. Quantum entanglement, spooky action at a distance. Maybe entangled particles are simply two objects sharing the same memory address in the cosmic code. Even the holographic principle, the idea that our three-dimensional reality is projected from a two-dimensional surface, fits neatly into this framework. Wormholes might be the seams where the projection folds back on itself, revealing the underlying grid of the simulation. But here's the twist: if wormholes are cheat codes, who's meant to use them? Some theorists speculate they could be relics of the simulation's boot-up phase, left over from when the programmers initialized the universe's conditions. Others propose they're intentional challenges, placed to see if any species evolves enough to reverse engineer them, a cosmic Turing test for civilizations. The most unsettling possibility, they're not for us at all. Wormholes might be maintenance tunnels for the simulators themselves, routes they use to tweak parameters or observe experiments without disrupting the simulation's flow. Of course, this theory blurs the line between science and metaphysics. Proving we're in a simulation is notoriously tricky. Any evidence we find could just be part of the program. But if wormholes exist, their very existence might hint at the universe's engineered nature. After all, natural processes tend toward chaos and inefficiency. Wormholes, with their precise balance of exotic matter and spacetime geometry, feel suspiciously optimized, like a feature designed for convenience rather than emergent from random physics. Whether simulation or not, the idea forces us to confront profound questions about reality's nature. If wormholes are shortcuts, what's the destination? And if we ever learn to traverse them, will we find the creators, or just more layers of the simulation, endlessly nested like a cosmic matryoshka doll? The answer might not lie in a telescope, but in the very fabric of the questions we're brave enough to ask. After 30 theories, countless equations, and decades of relentless curiosity, wormholes still guard their deepest secrets like cosmic sphinxes. The more we uncover, the more we realize how much lies beyond our grasp. Questions so profound they redefine what it means to explore. Take their very existence, despite the math allowing for them. No telescope has ever captured definitive proof. Are they hiding in the gravitational shadows of black holes, camouflaged by their own warped light? Or are they inherently unstable, blinking in and out of existence too quickly for us to catch? The answer could rewrite our understanding of reality, or reveal that nature has vetoed interstellar shortcuts altogether. Then there's the enigma of traversal. Even if we found a stable wormhole, could anything survive the journey? The tidal forces near its throat would shred conventional matter like tissue paper, while quantum effects might scramble atoms into unrecognizable forms. Some models suggest that only information-pure data could traverse intact, turning wormholes into cosmic telegraph wires rather than passenger tunnels. Imagine sending a probe through, only to reconstruct its scrambled remains on the other side like a puzzle with half the pieces missing. Would that still count as travel, or just high-stakes quantum faxing? But the most haunting mystery isn't how wormholes work, it's why they haven't reshaped the cosmos already. If they're possible, why hasn't some advanced civilization plastered the galaxy with them? The silence of the universe might be the biggest clue of all. Perhaps wormholes are rarer than we think, their formation requiring conditions so precise they've only occurred a handful of times since the Big Bang. Or maybe they're inherently destructive, collapsing into black holes the moment they're used, making them nature's version of a one-time only bridge. Solving these puzzles will demand more than bigger telescopes or faster computers. It'll require a revolution in physics itself. We might need to crack quantum gravity, the elusive theory that could unite relativity and quantum mechanics, revealing how spacetime behaves at the tiniest scales. Experiments with entangled particles or high-energy collisions could uncover hints of wormhole-like entanglement in the fabric of reality. Or perhaps the key lies in the cosmic microwave background's faintest whispers, where primordial wormholes might have left ghostly imprints. The beauty of these unsolved mysteries isn't just their complexity, it's their invitation. Every unanswered question is a door waiting to be kicked open, a challenge to rethink the fundamental rules of existence. Whether wormholes remain theoretical or one day become highways to the stars, their greatest gift might be the way they force us to confront the universe's boundless creativity. After all, a cosmos that keeps its greatest shortcuts just out of reach isn't being cruel, it's daring us to dig deeper. And that's a dare humanity has never been able to resist. From the moment Einstein's equations first hinted at the possibility of spacetime bridges, wormholes have captivated scientists and dreamers alike, not just as cosmic shortcuts, but as portals to entirely new ways of understanding reality. We've traversed 30 theories today, each more mind-bending than the last, from black holes masquerading as gateways to the holographic principles suggesting our universe might be a projection threaded with hidden tunnels. Yet for all the dazzling math and speculative physics, one truth stands out. Wormholes are more than just scientific curiosities. They're mirrors reflecting humanity's oldest longing to explore, to connect, to push beyond the limits of what we think is possible. Consider how far we've come. A century ago, wormholes were little more than scribbles in the margins of relativity papers. Today, they're at the heart of cutting-edge research, from quantum gravity experiments to simulations probing the nature of dark energy. The very fact that serious scientists can debate whether entanglement might be mediated by Planck-scale wormholes, or if exotic matter could stabilize a traversable tunnel, shows how radically our vision of the cosmos has expanded. These aren't just thought experiments, they're stepping stones toward a future where interstellar travel isn't confined to science fiction. But here's the beautiful paradox: even if wormholes remain forever out of reach, the pursuit of them has already reshaped our universe. The same math that describes spacetime tunnels has given us GPS satellites with pinpoint accuracy, revealed the existence of gravitational waves, and deepened our understanding of black holes. Every dead end in wormhole research has inadvertently opened new doors, proving that the journey matters as much as the destination, and what a journey it's been. We've seen how cosmic strings from the Big Bang might weave hidden shortcuts into the fabric of reality, how plasma infusion reactors could mimic the conditions needed to stabilize a wormhole's throat, even how consciousness itself might one day interface with these spacetime folds. Each theory, no matter how speculative, is a testament to human creativity, a reminder that science thrives not just on answers, but on questions that stretch our imagination to the breaking point. So where does that leave us? For now, wormholes remain tantalizingly out of reach, suspended between math and reality. But history shows that today's impossibilities are often tomorrow's breakthroughs. The atoms in your body were forged in stars that dared to explode, in galaxies that defied entropy to create something new. If the universe can turn stardust into storytellers, who's to say it can't bend space-time into doorways? As we sign off, remember, the greatest discoveries begin with a simple act of curiosity. Whether you're gazing at the night sky or diving into the comments to debate your favorite theory, you're part of this grand adventure. Keep questioning, keep wondering, and who knows, the key to unlocking wormholes might already be hiding in plain sight, waiting for the right mind to recognize it. Until then, the cosmos is full of mysteries worth chasing. See you out there. Don't forget to like, subscribe, and let us know which wormhole theory blew your mind the most. And if you've got a wild idea of your own, drop it in the comments. The next big breakthrough could start